Okay, so I'm back here with 52 weeks of AWS. It's been a little bit of a break. I needed to finish some work, but I'm going to take off where I left off before, which is the AWS security certification. So let's go ahead and get started with that. I'm going to go ahead and switch my screen here and get started. So in order to get started here, I'm going to talk about securing your infrastructure. And really, the idea here with securing your infrastructure is that you want to make sure that you're including all of the things that are important that are often missed. And well, let's go in and dive into the details here. So, first step here, we're going to talk about securing your infrastructure. And by the end of the module, you're going to be able to do the following things here: define the components of a virtual private cloud, also recognize account boundaries, and also describe Amazon Web Services that are available to protect your network and also the resources. So that's the agenda. And in terms of the overview here, you can see using a VPC, security groups, ACLs, using load balancers, etc. All right, so the first scenario here that AWS likes to bring up here is the concept of a bank business scenario. Always a good one to talk about for security. So the first thing that we're going to dive into here is a scenario. Let's say that we have somebody meeting with somebody else at the bank, and they realize that there are some security concerns that go beyond just the traditional, let's say, user access and management. And one of the things that is being discussed is an AWS migration. So what would need to be done? That's really the agenda here that's going to get talked about. So at the next meeting here, we have potentially a discussion of a VPC and how that could help apply multiple layers of security to support the network infrastructure. And this is really a good segue into the concept of a shared responsibility model. Really, maybe the most important slide of all with security is the idea of shared responsibility. So the idea here is that customers have some responsibilities and AWS has some responsibilities. The customer is responsible for the security in the cloud, and this would include customer data, platform applications, identity and access management, operating systems, network, firewall configuration, client-side data encryption and data integrity authentication, server-side encryption of file system and data, networking, traffic protection to include encryption, integrity, and identity. And now for AWS, it's responsible for the security of the cloud. This includes things like AWS Foundation services for compute, storage, databases, and networking, and also the AWS global infrastructure. And this would include things like regions, availability zones, and edge locations. So let's talk now about building out an application. And we can think of this as a 3-tier web application as a good thing to talk about. So if we get into what a 3-tier application looks like, for accessibility here, we have, a diagram of a 3-tier web application that has a presentation layer, a business logic layer, and a data storage layer. The VPC itself has 2 subnets in the availability zones, and the presentation layer includes 2 public subnets, one in each availability zone. So a subnet would then contain a security group with a host instance, and the other subnet has a NAT gateway. The application load balancer in this layer would then manage the traffic between the internet and also a front-end auto scaling group in the business logic layer. This way, the auto scaling group handles scaling for the front-end instances across the 2 availability zones. The network load balancer in the business logic layer then manages the traffic between the front end, which is the auto scaling group, and the back end auto scaling group. And then the back end auto scaling group would then handle scaling for the backend instances across the two availability zones. So the concept here is that a data storage layer would then hold a primary database in one of the availability zones, and then there's a read-only database in the second availability zone. And this data storage layer would then communicate with the backend auto-scaling group in the business logic layer. So this is a kind of a typical three-tier application to consider when you're building out a security scenario. So next up here, let's talk about a VPC and why that's so critical to security. So in terms of a VPC here, one of the things to consider is that you use a VPC to provision a logically isolated section of the AWS cloud where you can launch your AWS resources. The isolated section is called a VPC, or a virtual private cloud. The Amazon VPC is then going to provide a layer of control over the virtual networking. You can do things like select your own IP addresses, you can create subnets, you can configure route tables and gateways. You can also use both IPv4 and IPv6 in your VPC so that you can secure the resources and the applications. And you can also customize the network config of your VPC, and you can create a public subnet for web servers across the public internet. And you can also place backend systems like databases or application servers in a private subnet without public internet access. And then finally, you can use multiple layers of security in a VPC to control access to things like EC2 instances in a VPC subnet. And you also can have security mechanisms like security groups and network access control lists. So the idea here is that it's a layered measure of security. You're using more than one technique. So if we dive into the concept of a diagram of a subnet in a VPC, a region within the AWS cloud has one VPC, and this is spread across two availability zones. The VPC has one subnet in each availability zone, and a VPC is a virtual network that is logically isolated from the other virtual networks in the cloud, and the VPC is dedicated to a single AWS region, and it can span multiple availability zones. So after you create a VPC, what you would do next is divide it into one or more subnets. And a subnet is just a range of IP addresses that divide a VPC. Subnets belong to a single availability zone, but you can create subnets in different availability zones for high availability. And you can even make these public or private. So that's really the gist of a VPC. And if we dive into setting up public and private subnets and internet protocols here, this would be really the next evolution of what would happen. An internet gateway serves two purposes, and this is kind of a confusing term sometimes, but it's a target in the VPC route table for internet routable traffic, and it performs network address translation, or NAT, for instances that have been assigned a public IPv4 address. So the internet gateway would support IPv4 and IPv6 traffic, and it doesn't cause availability risks or bandwidth constraints on the network traffic. And also there's no charge. So the idea here is that you would enable access to or from the internet for instances in a subnet in a VPC. To do that, you would create an internet gateway and attach it to the VPC. Then you would add a route to the subnet's route table that directs the internet-bound traffic to the internal gateway. Then you would confirm that each instance in the subnet has a globally unique IP address, let's say a public IPv4 address or elastic IP address or an IPv6 address. And then you would confirm that the network ACL and security group would allow the relevant traffic to flow to and from an instance. So let's get into a NAT gateway here. The idea is that it's going to provide instances in a private subnet to connect to the internet or other services. And the NAT gateway also prevents the internet from initiating a connection with those two instances. So this is nice is that you're actually adding a layer of security so that people cannot make inbound requests to instances that you need to be secure. So this is just yet another layer of security. So to create a NAT gateway, you have to specify the public subnet that the NAT gateway should reside in. You also have to specify an elastic IP address to associate with the NAT gateway. So that's critical. After you create the NAT gateway, you can then update the route table and you can associate it with one or more of those private subnets you set up earlier that point to internet bound traffic. And then as a result, the instances in the private subnet can now communicate with the internet. Now, you also can use a NAT instance in a public subnet in the VPC instead of a NAT gateway, but a NAT gateway is a managed NAT service that provides better availability, higher bandwidth, and less administrative effort. So some of the things to consider here are NAT gateways, also NAT instances, and also, comparing a NAT gateway and a NAT instance. So if we talk about a private subnet here next, the idea here is that if you look at a diagram of a VPC with a public subnet and a private subnet, there are a few things to discuss. The first thing is that an EC2 instance in a private subnet would route traffic to a private route table and then a NAT gateway in the public subnet. So the traffic itself would then go to a public route table and then to an internal gateway. So if we break this down, what does it mean? All subnets consist of a contiguous range of IP addresses. So these addresses are not overlapping with other subnets in the VPC. The interfaces are also attached to EC2 instances in a private subnet, and they're not reachable from the outside. Also, if you're using AWS managed NAT gateways, EC2 instances can make outbound requests such as patching, and the response from the external resource would be allowed back in. Also, private subnets are often used to host database instances. So the reason for this is that you don't need to access a database through the public internet. Like there's no good reason to give somebody, let's say, direct SQL access to a database. Also, a NAT gateway must have an elastic IP address that is assigned to it. Now, if we get into a public subnet, things are a little bit different. In terms of a diagram with a public subnet from a VPC, the traffic from an EC2 instance in the subnet would go to a public route table and then to the internet gateway. And a few things to consider are when an external traffic needs to reach the interface, let's say it's an EC2 instance, the interface would require the following: a public IP address that's assigned to the EC2 instance and the subnet's route table that must include an entry to the interface. Once you have both of these, then the subnet is going to be considered a public subnet. So if we get into IP addressing here next, one of the things to consider is that IP addressing enables resources in a VPC to communicate with other resources over the internet. It's a network protocol. So when you reach a VPC, you assign a classless inter-domain routing or CIDR range to it, which is a range of private addresses. And the CIDR block might be as large as 16, which is 2 to the 16th, or 65,536 addresses, or it could be tiny, which is a 28, which is 2 to the 4, or 16 addresses. The CIDR block of a subnet can be the same as the block for the VPC that the subnet is in. And this means that a VPC and a subnet are the same size, and the VPC has a single subnet. So really, to summarize here, the CIDR block of a subnet can be a subset of the CIDR block for the VPC, and the structure supports the definition of multiple subnets. If you create more than one subnet in a VPC, the CIDR range of the subnet would not overlap. So you cannot have duplicate IP addresses in the same VPC, which makes sense to me. Now, in terms of reserved addresses, if you create a subnet it is going to require its own CIDR block. And so for each CIDR block you specify, AWS is going to reserve 5 IP addresses within that block, and you cannot use these 5 addresses. AWS reserves these because of the following reasons. 1, network address. 2, VPC local router. This is internal communication. 3, domain name system resolution, or DNS, future use, and then also network broadcast address. So a good example of this would be, let's say you have a subnet with an IPv4 CIDR block of 10.0.0.0/24. This is 256 total addresses. The subnet has 256 IP addresses, but again, if we subtract those 4, there's only 251 available because, or sorry, 5, there's 5 reserved for AWS. Now let's get into a public address here real quick. So the idea here is that, when you create this public address here, the VPC is going to get a private address automatically, and you can also request a public IP address be assigned when you create the instance if you modify the subnet's auto-assign public IP address property, and the public IP address will then let you, let's say, SSH into the machine. The public addresses, though, are dynamic. So if you stop an instance or start it, etc., you're going to get a new IP address. So if you do need to communicate with this public IP address, again, let's say for SSH or FTP server or something like that, you would have to use an elastic IP address rather than just blindly, assigning it a public address, because it's going to be disassociated as soon as you stop the instance. So that's kind of a big one that trips people up initially with AWS. Now, in terms of elastic addresses here, an elastic IP address is a static public IP address that's designed for dynamic cloud computing, and you can associate an elastic IP address with any instance or network interface for a VPC in an account. And an elastic IP address, you can mask the failure of an instance or software by rapidly removing the address to another instance in the account. So that's one option. Or maybe a better approach would be you can specify the elastic IP address in DNS. That way, the domain name would always be automatically associated. I think this is a better technique. So if your instance doesn't have a public IPv4 address, you can associate an elastic address with your instance to enable communication with the internet. Let's say you want to connect to it from your local laptop. The IP address that's elastic is static, and it's not going to change over time. And it also comes from Amazon's pool of IPv4 addresses, or from even a custom address as well. There is a charge with it, though, so that's something to be aware of. And also, when you use an elastic IP address, it's important consideration for, let's say, a long-term project, because if you're constantly having to worry about IP addresses, it's just really annoying to have to deal with that. So let's talk about an elastic network interface next year. The idea here is that an elastic network interface is a virtual network that you can attach or you can detach from an instance in a VPC. The network interface would then allow you to reattach it to another instance. So why would you want to do this? Well, if you move a network interface from one instance to another, then all that traffic would automatically redirect, which is pretty handy. Let's say you're upgrading the size of the EC2 instance. You don't want to have to reconfigure everything. You can just reassociate it. And each of the instances in the VPC has a default network interface. We'll call this the primary network interface. And this can be assigned a private IPv4 address from the VPC range. You cannot detach a private network interface from an instance. You can create and attach an additional network interface, though, to any instance in the VPC. And the number of network interfaces you can attach, though, varies widely. So you need to look at the specifications for the machine type. There are some circumstances, though, where you could have 2 network interfaces on an EC2 instance, and maybe you would do this for forensics, right? Where you could associate the network interface to a forensic instance, and then you could start looking at what's happening across, that machine because there was a security breach, etc. So the next thing we'll talk about is routes, route tables and routes. So if we look at a diagram of a public and private route table, the public subnet contains the EC2 instance and a NAT gateway. The NAT gateway, though, would direct traffic to a public route table and then to the internet gateway. The private subnet would then contain the EC2 instance where the traffic goes to the private route table. And then from there, the traffic is going to go to a NAT gateway and a public subnet. Now, the route table itself is a set of rules. So we call these routes, and these would direct the network traffic from the subnet. And then each route would specify a destination and a target. The destination is like the destination CIDR block where you want traffic from your subnet to go. The target is the target that the destination traffic is sent to. So this means that a routing table is just a simple lookup table that's going to keep track of things like paths, like a map, and it's going to determine where you're going to forward the traffic. So by default, every route table that you create is going to have a local route for communication with the VPC. You cannot delete that local route entry because it's used for internal communications, but you can customize a route table by adding additional routes. Each of the subnets should also have its own route table, and you're going to use the main route table of the parent VPC, which is the one that controls the routing for all the subnets that are not explicitly associated with other route tables. So the main route table is a route table that is automatically assigned to the VPC, and the main route table controls the routing for all of the subnets that are not explicitly associated with any other route table. And that subnet can be associated with only one route table at a time, but you can associate multiple subnets with the same route table. So a little bit of difficulty there in terms of the complexity of what's going on with the route table, but it is worth understanding this because that's really the fundamentals of how networking works on AWS. Now, some of the key takeaways here would be that a public subnet is used when external traffic needs to reach an interface, like an EC2 instance. Private subnets are used to host database instances that don't need to be accessed to the public internet. So again, this is probably a horrific, example of what not to do would be to have a database that can be exposed to the outside world. That's exactly the use case for a private subnet, and route tables determine where traffic is going to be routed to a VPC. So now that we've got through the networking, let's get into security groups, which are also reasonably complex here. So first step here, let's talk about the overview of what a security group is. So let's say we have a VPC with a public subnet and a private subnet. The public subnet would, let's say, contain an EC2 instance that's protected by security group 1. The private subnet would contain an Amazon relational database service, let's say, again, the database that's protected by security group 2. The only way you're going to allow these things to talk to each other is between the two security groups. So this is why the secure by design principle is working here, is that you actually have to connect those two resources through the security group, and the internet can only communicate with security group 1. So the security group is essentially a virtual firewall for the EC2 instance, and it's going to control both inbound and outbound traffic for the instance. And the security group would act at the instance level, not the subnet level. So each instance in a subnet in the VPC can be assigned to a different set of security groups. So really a high level way of thinking about this is a security group is a way to filter what traffic goes to your instances. So if we dive into this a little bit more here, let's take a look at what a security group is doing. In this particular example, we have a security group that doesn't have any inbound rules. So by default, the inbound traffic that originates from another host to your instance isn't even permitted until you add an inbound rule to the security group. So this is great. This is secure by design. And the default nature is that a security group would contain an outbound rule. So you can at least make a connection to the outbound world, but you can even remove this because you can add an outbound rule that can allow, specify, certain rules. So if your security group doesn't have any outbound rules, then outbound traffic that originates from your instance isn't allowed. And there's some use cases for this as well, depending on what kind of problems you're solving. The security groups are stateful, and this means that the state information is kept even after a request is processed. So what this means is that, let's say you send a request from your instance to the response traffic for the request, and you're allowing it to flow through regardless of the inbound security rules. Then the responses that are allowed to flow out are going to go regardless of the outbound rules. So this means that all rules are evaluated before a decision is made to allow traffic. And then the tables on this particular slide indicate that the inbound traffic is allowed from any network interface that's assigned to the same security group, and then all outbound traffic is allowed. So there's a lot of complexity as well with security groups, but the main idea here is, again, it's for filtering traffic to instances. So the key takeaways here are that a security group is essentially a virtual firewall that controls inbound and outbound traffic. The security groups are stateful, and this means that the information is kept even after a request is processed, and the rules are actually evaluated before a decision is made to allow traffic, which is a very, very secure setup. Now let's dive into next here using network ACLs. So yet another layer of security to add on top. So if we talk about a diagram here, this one shows how they work. Let's say a VPC has a public subnet and a private subnet, so similar to what was shown earlier. And the subnet would contain an EC2 instance. A network ACL in each subnet controls traffic to and from instances. So this is yet another way to do kind of similar things. The network access control list, or ACL, is an optional layer of security for the VPC, and it acts as a firewall to control the traffic in and out of one or more subnets. And then you can add another layer of security to your VPC. You can set up the network ACLs with rules that are similar to the security groups. So this would be having essentially a redundant layer of security beyond just the firewall, is you can also have a network layer of security. And so I guess the idea here is that you're going to be more resilient in case there was an accidental problem with one layer of your security, which is a good design. And each of the subnets in the VPC must be associated with a network ACL. If you don't explicitly associate a subnet with a network ACL, the automatic behavior is that it's going to be associated with a default network ACL. You can associate a network ACL with multiple subnets, but a subnet can be associated with only one network ACL at a time. And when you associate a network ACL with a subnet, the previous association is actually removed. So let's talk about a diagram here as well. So a network ACL has a separate inbound and outbound rule, and each rule is either allow or deny traffic, and the network ACLs are stateless. So this means that responses to inbound traffic are going to be subject to rules for outbound traffic and vice versa. And the VPC is automatically going to come with a modifiable default network ACL. So by default, everything goes, right? It's inbound and outbound IPv4 traffic. And if you have IPv6, that would be set up as well. And you can see in this particular diagram that a default network ACL for VPC supports IPv4 only. You can create a custom network ACL and associate it with a subnet. And by default, each custom network ACL would deny all inbound and outbound traffic until you add the rules. And these rules are evaluated in a number order before a decision is made to allow traffic. So the network ACL is going to include a rule whose rule number is an asterisk. And this rule ensures that if a packet doesn't match any other rule, it's then denied, and you can't modify or remove this rule. So that's also an important thing to consider. That's an optional but advanced form of security. So if we look at how this compares, in terms of security groups and network ACLs, because there's some similarity and confusion, often between these two things, is that a security group acts at the instance level, let's say a database or an EC2 instance or interface level, but the network ACL acts at the subnet level. And the security group allows rules only, but network ACLs allow support both allow and deny rules. And security groups are stateful, but network ACLs are stateless. And then security groups are set up so that the rules are evaluated before the decision is made to allow traffic. For network ACLs, rules are evaluated in a number order before the decision is made to allow traffic. So let's talk about some features of a VPC here. So that's the main container, right? So we have, the holding mechanism for both of these is a VPC. And so an EC2 instance is surrounded by lots of layers of security. That's the best way to think about it. The closest layer to the instance is the security group. If you peel the onion back a little bit, the next layer of security is the ACL. The outside and the farthest layer is the subnet routing. So if we look at a VPC, what does it have? It has a security group which acts as a virtual firewall for the EC2 instances, and this controls the inbound and outbound traffic. The network ACL provides an optional layer of security for the VPC, and this acts as a firewall to control the traffic in and out, but at the subnet level. The subnets make the network more efficient. So, through subnetting, the network can travel a shorter distance because you're going to limit unnecessary hops. And the route table itself is going to control where the network traffic is directed. With something like VPC flow logs feature, you can even capture the information from the IP traffic going in and out from a network interface in your VPC. And then you can even publish that data to AWS CloudWatch logs or even to S3. And then you can actually look at that information and analyze it. You can also create a flow log for a VPC subnet or network interface. If you create a flow log for a subnet or VPC, the network interfaces in that subnet or VPC are then monitored. So really, flow log data is a great way to record exactly what's happening and kind of dig into the details of network analysis. So let's talk about some key takeaways here for using the ACLs here. Key takeaway number one is that network ACL is optional. You don't need it, but it is an additional layer of security for your VPC, and it acts as a firewall to control traffic at the subnet level. Also, each subnet in your VPC must be associated with a network ACL. The network ACLs are stateless, so this means that a response to inbound traffic is subject to the rules for outbound traffic, and also rules are evaluated in number order. All right, so what do we got left here? Let's talk about load balancers now. So load balancers are also a very complex topic. Let's dive into it and talk about how traffic is going from, let's say, a user to an application load balancer. Here, the traffic is going to get split between two EC2 instances. So this service would automatically distribute the traffic across multiple targets. The targets could be an EC2 instance, it could be a container, it could be an IP address. So that's something you would configure. And the listener is a process that checks for connection requests. The ELB, or Elastic Load Balancer, is going to scale the traffic over time because the vast majority of workload is going to be handled automatically. And this means that it's going to increase the availability and fault tolerance of your application. So in general, this is even beyond computers, right? You want more than one thing for redundancy. Spare tire, for example. So you can add and remove instances from your load balancer as your needs change. And this won't disrupt the flow of requests because the load balancer itself can redirect traffic to the instances that are actually available. And you can also configure health checks, which monitor the health of the registered targets as well. So there's a lot you can do here with load balancers. Now, if we get into data protection with an ELB, the main idea here is that you have a single point of contact. So a load balancer would serve as this contact. Also, the load balancer can secure HTTPS communication. So you're getting encryption by default. And really what this means is you're getting encryption both at rest and at transit. So if we talk about how these would work in action here, the internet traffic is going to go to the gateway, to the availability zone, to the load balancer, and then it's going to serve secure traffic to a private subnet. Really, that's the high level overview. So if we talk about this from a key takeaway perspective, an ELB is going to distribute the traffic across multiple targets like instances, containers, IP addresses, or even Lambda functions. And the ELB can handle a wide variety of application traffic in a single availability zone or even across multiple availability zones. And you can add and remove things as needed without disrupting your application. So it's a pretty big feature here. So let's go ahead and wrap things up here. If we talk about securing your infrastructure, I think the big thing to consider is that a load balancer and VPC works together. And a VPC, as we talked about, has all these subcomponents and these sub layers of security. So the main takeaway is that to protect your network, you want to control the traffic at all of the layers. You want to use things like inspection. You also want to use threat intelligence and anomaly detection. And in general, you want to limit the workload to the internet. You want nothing exposed that should be internal. And the internal network is only going to be communicating with resources that you've carefully designed here. If we also talk about the compute resources, there's some things to consider as well. There's something called Amazon Inspector. And what this does is it runs automated security assessments on EC2 instances. So this is another great tool to improve the security. We also have some concepts here like automated tasks, for example, regular monitoring of the resources, and even you can integrate this into a DevOps type workflow as well. There's also AWS Systems Manager, and what this does is it gives you the visibility and control over the infrastructure, and you can collect things like a system inventory, operating system patches, et cetera. So this is important because if somebody manually changed one machine, you can look at the inventory and say, hey, why is this one machine changed, which often can mean that there was a breach of that particular piece of hardware. Now, if we talk about key takeaways here, the inspector is automated security assessment, and it gives you visibility over the infrastructure and even lets you scan for resources that have been compromised. So in a nutshell here, that's a pretty deep topic, actually, the network security level, but I think all of it has been covered in a fairly comprehensive way. And thank you for staying tuned here. Next week, I'm going to talk about the next section of network AWS security certification, and see you then.